Right, I wanted to look a little more at today nuclear sizes, and then also we'll look at some practical applications of nuclear energy and acceptable amounts of radiation that the human body can absorb. And then finally, we'll look at the history of the nuclear power and its relationship to the design of our first atomic bomb. Okay, and so this is all associated with the material from chapter 43, and one of the first subjects that's covered in chapter 43 is this nuclear sizes stuff. And so I wanted to look at this just a little bit to give you a feeling for how insensitive the size of the nucleus is to fairly large changes in the atomic mass number. And so the way that I wanted to start with this is to first of all define a nuclear density. And so this tends to be about the same for all atoms. And this is just the mass of the nucleus divided by the volume of the nucleus. If we assume that this is a uniform sphere, then the mass is proportional to the atomic mass number, and it's actually, this k value would actually be essentially a mu value. It would be like the mass of a proton or the mass of mass either of a proton or a neutron. So it should be, k would be here would be about 1.67 times 10 to the minus 27. And then this would be divided by the volume of a sphere that has a radius that's equal to the atomic radius, or the nuclear radius. Here, the nuclear radius. So the nuclear radius is on the order of femtometers. And so if we take this equation and solve it for r, we see that r then is related to the cube root of all these other things, Ka divided by 4/3 pi density. But that's just some other constant. I'll call it K prime here. It's equal to the mu divided by 4/3 pi times the nuclear density, which is, as I said, roughly the same for most nuclei, times the atomic mass number to the 1/3 power. So remember here, A is equal to Z plus N. Proton number plus neutron number. So this is our atomic mass number. So when you evaluate K prime, we get that it's 1.2 femtometers, or that's 1.2 times 10 to the minus 15 meters, times A to the 1/3 power. So the units then for R in this calculation would be femtometers, and not regular meters, of course. And so let's just try this then with a couple of values for A. Let's say that A is equal to 1, which would be for hydrogen. Then R would be equal to 1.2 femtometers. What if A was equal to 12 for the carbon nucleus? Okay, then R would be equal to 1.2 times 12 to the 1/3 power. Okay, and so it doesn't grow as fast as you might think it does. The radius here, 12 to the 1/3, is just 2.28 times 1.2 is 2.74. So here we've got something that has 12 times more particles in it, that is only 2.74 times the radius. So we see that the radius isn't increasing that fast. What if we go to U-238? 92, 146. Then R, here would be 1.2 times 238 to to the 1/3 power. That'd be about the biggest radius that we can get that's associated with the range of the strong nuclear force not being overwhelmed, as we mentioned before. That would just be 6.18 femtometers. So just a little more than 6 times the radius of a hydrogen atom. And so this is why it's possible, even though the strong nuclear force is so short range, we can still squeeze a lot of stable atoms in to that very short distance, because the radius increases so sluggishly with the increase in atomic mass number. Okay, but this is pretty much it. You know, you get bigger than this, which we can do. You get half-lives that get progressively smaller. And so in a supernova explosion, as you saw in the last astronomy video that I recommended that you watch, those supernova explosions can produce elements that are super big, like element number 257, you know, but those don't last very long because they exceed the range of the strong nuclear force, and so they might only have a half-life of 1/1000th of a second before they decay down into smaller elements, ones that are observable on the periodic table. But still, this gives us maybe a little bit of a feeling for how the nuclear sizes change as a function of A. Next thing I wanted to talk about is the natural radioactivity sequence. Now, in a sequence of natural radioactivity reactions, we usually are just emitting a small particle, like either photon, which is really small, or a electron, or an alpha particle. Or sometimes there are other slightly more complicated processes in which we're, say, absorbing a positron or emitting a positron. There's also electron capture. So there are a few other things that I haven't mentioned that aren't principal types of radioactive decay, but are important in certain applications. Okay, so let's keep in mind, though, that normally for natural radioactivity, we either have an alpha particle or a beta particle emitted. And the reason why one or the other would be emitted can be seen by looking at an N versus Z plot in which we have a slope for large values of Z here, where the slope is equal to 1.5. So we've talked about this a lot before. This tells us that there's 1.5 neutrons for every proton. And so we can see then that thorium, with a little higher value for the N to Z ratio than 1.5, can decay by an alpha decay into something that's a little lower, but that alpha decay process, in this case, would bring it down along a diagonal in which the number of neutrons would decrease by 2, and the number of protons would also decrease by 2. And so then, once it gets to radon, though, we see that at that point, or radium, I should say, sorry, that it's even higher N to Z ratio. So even though that reaction might be favored, it results in a couple of beta decays. And the beta decays lower the N to Z ratio until finally it crosses over and it overshoots. Okay, so we go from thorium to radium, and then we emit 2 beta particles, and that brings us back up to thorium again. Because remember, each time you emit a beta particle, you have an increase in 1, so you go from radium back up to actinium, which is element number 89, and then back to thorium again, okay, which is element number 90, but a lower mass isotope. So the N to Z ratio now is lower. Okay, but what does alpha want to do? It wants to raise the N to Z ratio. And so it kicks off another alpha particle. So now it's a lower mass isotope of radium. So it's still directly below the value of radium before, but with a lower value for N, but with the same value for Z. And so then it would tend to decay a couple more times along this diagonal line, because it's going 2 down in N, 2 down in Z. Similarly here. But then it goes along this diagonal line because it goes up 1 in Z and down 1 in N. Okay, so that's why a diagonal line goes this way, because you're increasing Z by 1, but decreasing N by 1. And so what we tend to get then in a natural radioactive sequence is a whole series of these alpha and beta decays that try to keep the element fairly close to the optimum line that corresponds to the slope of 1.5 in our N versus Z curve. And so small particles are emitted, and so it tends to work along this kind. So this is our alpha decay, this is our beta decay, maybe another beta decay here, then another alpha, then another alpha, and maybe another alpha, then a couple more beta, then another alpha, and then finally it reaches a point of relative stability. And so this could start all the way up at, for example, U-238. And then finish, and this is a typical kind of a radioactive sequence because U-238 has a larger half-life than lead-206. So this would be the starting point in our natural radioactivity sequence, and then this would be the finishing point here at lead-206, tending to stay close to that 1.5 line, but then correcting by either alpha decays to move it along this diagonal line or beta decays to move it along this diagonal line, while all the time keeping close to our slope of 1.5 until it reaches a point of relative stability. So you might wonder then, well, why isn't that point then iron? Well, lead is relatively stable, and so even over the lifetime of the solar system, it may not decay much. But eventually this would keep going and work its way down to iron if we could wait long enough, and that would be the absolute minimum, whereas this would be a relative minimum in the curve that is consistent with the age of the universe and the half-lives of these materials. Now, U-235 also has a decay sequence, but the half-life for U-238 is about the age of the Earth. Actually a little longer than the age of the Earth is the half-life for U-238, whereas the half-life for U-235 is about 700 million years. Now remember that U-235 is pretty easy to bust apart. And so this is what we use to make our atomic bombs, both U-235 and plutonium-239. Were our two principal sources of fissionable material that we used to make the atomic bomb back in World War II. But U-235 is rare on the Earth. It's less than 1% of the total amount in a radioactive sample. Why? Because its half-life is shorter. This still seems like a long half-life. 700 million years is a long half-life. But if we divide this into the age of the Earth, we see that, well, 7 times 5 is 35. 7 times 6 is 42. So it'd be like 6 half-lives have gone by. So that means that you're looking at 2 to the 6th power. 2, 4, 8, 16, 32, 6. So it'll be 1/64th as much of this now as there would be here. This has just been cut in half. Okay, so this has been cut by 64. So there's a difference here in how much U-238. This is greatly dominates, and when you work it all out, we find that there's way less than 1% of a uranium sample is U-235. But nevertheless, U-235 also decays along a similar kind of a decay sequence of alpha and beta decays, but to a different isotope of lead. Okay, so if we were just doing a rough calculation here, we could say that the half-lives of all of these other processes are fairly short, so that the main process of turning U-238 into lead-206 happens basically, the rest of these, once the uranium decays, the rest of these happen almost instantaneously, because the half-lives of all the rest of these reactions are short in comparison to the age of the Earth. And so in this process, let's say that there are, and this turns out to be the correct value, by the way, 8 alpha decays. And a certain number of beta decays. Now it turns out that we can figure out the Q for this reaction without even knowing how many beta decays occur. And the reason for that is the Q for a beta decay does not depend on the mass of the electron. Okay? Remember that the mass of the electron, say in a beta decay process where the electron is ejected out, you also have because a neutron is turned into a proton, you have Z+1 protons in here. So that's going to attract another electron into its outermost orbit. And so it's not the same electron that's been ejected out, but the electron masses cancel because you have one extra electron orbiting in the outermost shell because you have Z+1 protons. And so you don't care then, when you're figuring out the Q reaction, how many beta decays have occurred. But we do have to account for the alpha masses. And so if you take all of the different reactions, all the different alpha-beta decay reactions, and add them together, what you end up with is U-238 goes to lead 206 plus 8 alpha. Okay? Where the alpha is going to be 2, 2, 4. And that's all you need to find the total Q value for this reaction. And you can assume that it happens as quickly as one of the uraniums decays. All the rest of these things happen at a lifespan that's much shorter than the length of the Earth. So you can assume then that if you have had some uranium-238 in this sample, that almost instantaneously then turns into lead-206. And so how much lead-206 you find in relationship to how much uranium 238 was in at the beginning, it would be a way then that you could determine the age of the Earth. And so in this process, the Q would be equal to, now which one has more mass? Well, the uranium is going to have more mass because when these particles result from the decay of uranium, that's going to give off energy. And so that energy then is related to the Q value. So that's going to be the mass of the U-238 times C squared minus the mass of the lead-206 minus 8 times the mass of the alpha particle, 224, all times C squared. Or we can rewrite this as, let's do it over here, Q equals, and here I'll need to pull out my tabulated values. For U-238, that's going to be 238.05786 mu minus lead-206 mass. That's going to be 205.97404 minus 8 times the mass of an alpha particle, because there are 8 total alpha decays in that natural radioactive sequence. So that's 4.002603. This is mu. There's a mu in there too. And then that's times C squared, which again is 931.5 MeV over mu. Mu's units cancel, and we get a value for Q, which is 51.7 MeV. By looking at the relative amounts of lead-206 to U-238, we can find the age of the Earth. If, and only if, we can find a sample that's been undisturbed for the entire age of the Earth. Now that's tough to do, because where are you going to find a sample that is completely undisturbed for the whole lifespan of the Earth? I don't know, but if you went and you looked at an asteroid, you would assume that material is made out of the same material that the Earth is. And so if you could find some kind of a mineral structure that had some uranium in it, and you could get a pristine enough sample of that that hadn't been disturbed over, and you were able to pull this number up several times from different meteors and or from dating material that you find on the moon, then that would be strong evidence that you might have the right number. But to date something, you need to be able to use something that has a half-life that's comparable to the length of time that you're trying to measure. So this wouldn't work with carbon dating. In carbon dating, you have a sample like carbon-14, this would be 6, 8, and that tends to go to nitrogen-14, 7, 7, 14, plus a beta particle. And so the half-life of that reaction, because it's a beta decay reaction, is about 5,000 years. So this then is perfect for doing paleontology with humans that were like the Iceman from 3,000 years ago. Or, you know, if you can go through a few half-life time periods, then you're still okay with carbon dating, so you could go back to Neanderthal. But, so this is good then for timescales on the order of tens of thousands of years. But not good for the age of the Earth, because the age of the Earth is way too many 5,000-year time periods, and there'd be not enough measurable carbon left. Now, how do we get carbon-14? Well, carbon-14 comes from the sun blasting and adding neutrons to nitrogen atoms in the upper atmosphere. Okay, and so you can actually produce carbon-14 out of nitrogen-14 with the help of the sun. And the sun's energy then, cosmic rays in particular, can produce neutrons. And those neutrons can then interact to produce carbon-14. Now, as long as we have living creatures that are taking in the carbon, and so we eat the carbon that is produced by plants, and the plants take in the carbon in the form of CO2 during photosynthesis, then that means that the amount of heavy carbon in all living creatures should be about the same. But then once the organism dies, it stops taking in more of the enriched carbon-14, and that carbon-14 starts to decay. And so this tells us then, this gives us a clock on how long since the organism died. Right? And so with that idea in mind then, we can go back to this idea of carbon dating, and we can see then that we have something that's a relatively accurate clock, as long as the intensity of sunlight and the amount of heavy carbon has remained constant over geologic time. And so that's probably approximately true over at least a few thousand-year time period. We know that the sun has gotten hotter, but more on the order of maybe 10% every billion years. Okay, and so in the amount of time that we might be measuring the age of something using carbon dating, this is probably fairly accurate. So we're just measuring then the relative amounts, and then we can go back to our half-life equation and figure out how much of that material we would expect after a certain length of time. You can solve for the time. That gives you the age of the sample. Next thing I wanted to look at is ways of measuring radiation intensity. And so one way of measuring it is in terms of a total amount of radiation that's absorbed per unit mass. Okay? Because if I'm twice as big as somebody, I'm going to get twice as much radiation. But each of my kilograms of mass is going to get roughly the same. And so radiation dosage is usually measured in terms of an energy per unit mass. And so we define 1 rad as being equal to the total energy of 0.01 joules absorbed in a kilogram of mass. So let's say that I received 1 rad, and so the total amount of energy absorbed then is going to depend on how much mass my body has. So total energy absorbed if the mass, let's make a nice easy number here of 100 kilograms for the total amount of mass that is absorbing that 1 rad of radiation would be equal to 0.01 joules per kilogram times 100 kilograms. That means 100 kilograms of mass that receives 1 rad of radiation is going to get 1 joule of radioactive energy absorbed. So what form is that going to take? Well, it's going to take the form of high energy protons, or typically not necessarily protons, but high energy alpha particles. Could be high energy neutrons too, because neutron radiation is actually a particularly damaging kind of radiation. Could be high energy electrons. You also do have high energy protons. There's a new kind of therapy called proton therapy, in which you blast a certain tumor with this proton radiation, and it goes right through the material without damaging it very much, and then with a certain energy it just damages the tumor without damaging the material between the tumor and the outside of your skin. And so that's a really promising kind of therapy that actually does use proton radiation. But typically this radiation might take the form of beta particles, alpha particles, or neutrons. And so that's 1 rad. And that's an absolute amount of radiation that is absorbed. Okay. Now, we have here, if we're going to connect rad to larger amounts of radiation that could be absorbed, then we would be looking at a gray. So gray then is sometimes given the symbol G, and that's 100 rads. Or that's the same thing as 1 joule per kilogram. So if you get 100 rads of radiation, that's considered to be fairly dangerous. One to 100 to 400 rads can be fatal. Isn't always, but at that intensity, you're getting to the point where people may end up getting some kind of radiation sickness right away, but it could also result in cancer, let's say, in 10 or 20 years. Okay, and so 4 grays then would be considered to be a big chunk of radiation, and that would be an unsafe dosage. Okay, but not all radiation is born equally. We have certain particles that have more of an effect on the human body than others do. And so there's what's called a RBE that connects in the idea of a REM with a rad. So REM then is related to a rad, by what's called the relative biological equivalent. And so this REM then is, includes the destructive effects on humans of the radiation. And so REM then is equal to your relative biological equivalent times your rad number, where RBE is the relative biological equivalent, and this gives you the destructive influence of a particular type of radiation. So for example, and we could set up a little table here. And by the way, these numbers aren't absolute. They depend on the energy of the particle too. That if we have the type of radiation here, and it's RBE here, we see that certain types of radiation are about the same in terms of RBE. So for example, a photon, gamma ray, has an RBE of 1. An electron has an RBE of 1, roughly speaking. So that means that the number of REMs and the number of rads are the same then for electrons and for gamma ray photons, assuming that you got the same amount of radiation in each case. But for alpha particles, we're looking more at something like 20. Okay, so alpha particles are going to rip right through you. And so just imagine, if I have a little bullet fired through that wall, and then you have a big cannonball fired through that wall. What's going to do more damage? Even if they both have the same energy, I think you might agree that the cannonball would, because it's going to just rip right through everything. And so that's what the alpha particle does. It's got a mass that's way more than the mass of the electron, maybe 8,000 times more mass than the electron. And it's going to just tear through you and do horrible amounts of damage on its way through. And this depends again on how energetic the radiation is, how much RBE it has. So this number can fluctuate a little. It can be as low as 12, but it can be much higher too, depending. And then neutrons are the worst of all. They're like 30. And the reason for this is that neutrons, although they don't weigh as much as alpha particles, they're not deflected by the positive nuclei. And so they can just rip right through things. They were like our nuclear probe before, when we were trying to make elements get bigger and stimulate a fission reaction. We could do that because the neutron didn't get repelled very much by the nucleus. And so that means that the neutron can go just ripping right through the nucleus as well. So we get considerably higher RBEs. And so they've actually talked about neutron bombs, in which you have a small amount of energy, but it does 30 times more damage to the body. Let's say, for example, an atomic bomb. And so there's lots of neutrons that are produced there. And so they could just rip right through things, people, and hurt the people, and then the structures would remain intact. So this is something to keep in mind then when you're talking in terms of REM versus RAD, is that the REM includes the effect of the RBE, which means that this is the essentially a scaled version of the RAD in terms of how much damage it does to the human body. Okay. And then 100 REM equals a Seifert. So Seifert then is kind of the equivalent of a gray in RADs. 100 RADs makes a gray, 100 REMs makes a Seifert. And oftentimes we consider normal background radiation to be on the order of, say, 3 to 6 millisieverts. Per year. So this is what we would consider to be a normal background kind of radiation on the order of millisieverts. Okay, so that would be essentially the same thing as 0.1 rem. Okay, but oftentimes it is expressed in terms of millisieverts. And of course that makes things a little bit complicated because we're using several different sets of units here. But one thing that's important about the radiation intensity is that it follows an inverse square law. And that this is absolute radiation and not a decay rate. Okay, now in terms of decay rates, these are often written in terms of Curies. So decay rate then is number of decays per second. So 1 decay per second is called a becquerel. And 1 Curie worth of radiation is 37 billion becquerels. Or this is the same thing as 37 billion decays per second. Now a Curie has to be defined in terms of being a certain distance away from a radioactive source. So for example, if you took a source of radium and you were a certain distance away from it, then you would get a certain amount of radiation. But the radiation follows an inverse square law. So the total radiation, if it's spherically symmetric, follows the inverse square law. Meaning that if you get twice as far away from a source of radiation, that would have associated with it only 1/4 as much radiation. And so let's say you had some huge amount of radiation going off, like an atomic bomb. So this thing blows, and then at the surface of the Earth, nearby to the atomic bomb, let's say that your intensity down here, in terms of the total amount of radiation you would receive, might be on the order of 10,000 rad. And so that's nearby to the explosion. Then if you go out here, let's say 10 times farther, so this, let's say this distance is d, and this distance is 10d, and this is following an inverse square law, then the intensity of the reaction, or the radiation, out here is only going to be 1 over 10 squared times the radiation at a distance d away, which is 10,000. So typically you might get 10,000 rads of neutron radiation, 10,000 rads of alpha radiation, and beta radiation. You get all of it nearby to, and an atomic bomb would tend to blow up a certain distance above the surface. With the bomb that blew up in Hiroshima, they actually had this thing all set up so nicely with little hills on either side to help reflect the energy inward so that they could really show how big of a bomb this was. And then the Japanese were saying, we do not know what the nature of these bombs was. Then we had to tell them that it was just a single bomb that did it. It wasn't a whole bunch of bombs, and they thought it was. It's a whole bunch of them. But here, this is 10,000 rads, and so this means that people in this nearby area, if 100 rads can kill you, then this would be 100 times that. But you get out here, and you're all the way down at 100 rads. Because of the inverse square law, 10 times farther away, you're only 1/100th of 10,000. And so this is survivable here at a distance that's 10 times farther away. So that might be a few miles away. So if you're, say, talking on your cell phone and you're worried about that kind of radiation, it turns out that kind of radiation isn't as bad because it's not ionizing radiation. This is microwave radiation. And you don't get to ionizing radiation until UV. So non-ionizing radiation is any kind of electromagnetic radiation with a wavelength that is greater than about 400 nanometers. So for lambda less than 400 nanometers, this is ionizing. So this is ultraviolet radiation because that's the next level of radiation above visible. And so that's the kind that can do the most damage to human tissue. This is not to say, though, that you won't get some kind of damage from listening or talking on a cell phone and this thing held right up to your ear like this, because this is the same kind of energy that is in a microwave oven. And so that'll cook your brain just a little bit. So that's something that you want to be cautious of, is that the distance of the phone, let's say away from your head, if you move it from 1 inch away to 15 inches, then the amount of damage that's being done, if we don't know what the damage is being done, but if you're being cooked a little bit, maybe some damage is being done, that's going to be 1 over 15 squared, or what's that, 225 or something, times less damage being done if you held it out at arm's length and have the thing set to speakerphone. Okay, so it's very important then that we are clear as to how a spherically symmetric source of radiation damps off or decreases with distance. Now this can be used to our advantage if we are treating certain types of tumors. Let's say you have a near surface tumor. Then you might want to blast it with alpha particles, okay? Because the alpha particles are going to do a lot of damage to this area, but they don't penetrate very far. The penetration depth is small. However, if you had, let's say, you're trying to treat a tumor in the middle of your body, then you don't want to use alpha anymore because it's going to do more damage out here, and it's going to do less damage as it moves farther along. That's where the proton radiation is so encouraging, because that can do less damage, almost like magic with quantum mechanics. You can tune it to a certain distance away and then increase the amount of damage it does there. But typically what you're more interested in here is beta radiation or gamma. And with gamma, what you can do is you can fire photons at different angles, and you can intersect this, because gamma can go through 6 feet of lead, the most penetrating. And so you can do a little damage here, a little damage there, but a lot of damage there. So gamma treatment, that's the most penetrating, is better for deep tumors. Whereas the alpha particles with a small penetration distance are good for near surface tumors or for implants. Say, for example, you have prostate cancer. Then what you could do is, because the prostate is pretty far in there, you could put little radioactive beads in there. So you could pepper the area with these, and then if they're producing alpha particles, then the alpha particles are going to do a lot of damage in the vicinity of the tumor, but then by the time that we get far away from the tumor, the alpha particles don't have much penetration. And so that means that it doesn't destroy all of the tissue that's around it. And so this is an important kind of a tool then for making use of the fact that the alpha particles do a lot of damage. Remember, they have a high RBE, but they also don't penetrate very far. Their penetration depth is the least, because it's like a cannonball going through a big barrier and then being slowed down on its way through. So it does a lot of damage, but kind of crashes and burns to a stop relatively quickly. And so these ideas then are inherent in a lot of the treatment processes for different kinds of tumors. And so this is where the use of radiation can be effective. Now, in a less constructive note, we can look at how an atomic bomb was created. And so this was done to combat against what we felt was a threat from Adolf Hitler during World War II. In 1937, Einstein sent a letter to President Roosevelt, and he was coerced to do this by a lot of scientists, but he was sympathetic because, of course, Hitler wanted to kill all the Jews. And unfortunately for Hitler, most of the really smart physicists were Jewish. And so they kind of banded together and were highly motivated to keep Hitler from conquering the world with nuclear weapons. And so we started the Manhattan Project. So the idea then with our construction of the atomic bomb was there were two different sources for our fissionable material. We talked about fission a little earlier, remember. You have a neutron comes in, it strikes either a plutonium atom or a U-235. These are the ones that are easiest to bust apart. And then that breaks up into several atoms, and then you have several neutrons that move away. And those neutrons can then interact with other, either plutonium or uranium atoms, and then this can create an ever-escalating explosion. Now, if you can control this reaction so that you don't try to keep the number of neutrons under control, then if you do try to keep it under control, then you can get a nuclear power plant. And so we'll talk about that in a few minutes. But the two sources of fission materials were the plutonium 239, and I showed you the reaction for how this was built up in nuclear power plants before, and the uranium 235. And so this had to be mined, and this had to be produced in nuclear power plants. And so Enrico Fermi was the person who first got nuclear power plants going, and he realized that you could produce plutonium in a nuclear power plant. And so they stopped their production of nuclear energy, and they dropped everything they were doing and started trying to make more of this plutonium. And the other source of fissionable material was U-235. They thought that might also work. And so that had to be mined. And so that was kind of a chemical diffusion process in those days. Today, we can use centrifuges, and that is a much more effective way to distill out the U-235, which is less than 1%, as we talked about before, of a total sample, because the U-235 has a lower half-life. So we have to mine this and extract the small amount of U-235. And so they, at the Manhattan Project, they didn't have either one of those raw materials at first. It took a couple of years to make the right amount of it. Turns out that you need something like 15 kilograms of this material to produce an atomic bomb. Or at least those were the numbers at the level of purity that you could get at that time, which is about 70%. And so our competitor for the atomic bomb was Heisenberg, the guy from the Heisenberg uncertainty principle. They got Heisenberg to run the German atomic bomb project. And so he made a mistake in his calculation of how much fissionable material was necessary to create what's called critical mass. And Heisenberg estimated that you need about 50 kilograms. And with 50 kilograms, it would take about 10 years to gather that much. But 15 could be brought together in a year or two. And so with the correct numbers, we were able to get the right kind of material going in a reasonable time frame. Now, the whole key to making this work is what we call critical mass. And so for critical mass, this is the point of concentration where the number of neutrons produced divided by the number of neutrons consumed is much, much greater than 1. And so this happens then as one uranium atom, say, has 3 neutrons come off from it during our fission process, and then another one has 3, another one has 3, and then those can combine with others. And so if we can produce more than are consumed, so here's a neutron coming in that's consumed in this reaction, but if we have a lot more being produced, then we can get a bomb. Okay, and so this turns out to happen when the total concentration is around 15 kilograms. And so the atomic bomb, the strategy then, is to get a mass that's just below critical mass, because you don't want it to just blow up on its own. You want to be able to control when it blows up. And then fire something into it that brings it up to critical mass. So how do we do that? Well, there's 2 competing methods. One is called the gun method. So here in the gun method, you have a radioactive bullet. That's fired into a mass here that is near critical mass. So you fire the bullet, and then that brings the mass above critical mass. And so then it blows up. So we get it just close enough to critical mass so that when this thing buries itself in, it pushes it over that line. And then suddenly the number of neutrons produced divided by the number consumed goes exponential, and the thing blows up. The problem was, this didn't work for plutonium. And plutonium was the first material that the scientists got at Los Alamos to work with. And so the reaction didn't go by fast enough. The bullet couldn't keep up with how fast the reactions had to go as this thing buried itself into the near critical mass. And so Richard Feynman came up with another idea. Feynman's idea is to have plastic explosives to cause implosion. So here are plastic explosives, and then here's our plutonium core that's near critical. So the idea then is that these explosives could be focused in such a way as to push down on the plutonium core. And so this focusing process had to be done electrically. So you had to have capacitors in here that could control when the different explosions could go off, because you needed a perfectly symmetric blast wave that could push in. It's like a balloon. If you try to push in with a balloon from a couple of directions, then the balloon will slip out unless you've got a perfectly spherical way of pushing down on that balloon, then it'll just slip out through the edges. And so this was way beyond the abilities of the scientists that were there to figure out how to make an explosive shock wave that's symmetric. And you would think maybe that it was impossible, but they were actually able to do it. And so this worked. And this then also became the basic guiding principle for how a hydrogen bomb would work too. Because in a hydrogen bomb, you need to have a high enough temperature. And there was nowhere on Earth that you could get high enough temperatures until the invention of the atomic bomb. And so then you use that as the trigger that it's like striking a match to get it going. The energy of activation was necessary for the hydrogen bomb from using the atomic bombs instead of plastic explosives around a hydrogen core. And then eventually they were able to develop these bombs that were 1,000 times more destructive than the ones that were dropped on Hiroshima and Nagasaki. Those are the hydrogen bombs, which we'll talk about after the midterm. But then finally, some U-235 came in, and they found that the gun method does work for U-235. And so they had two different types of bombs now. They had the plutonium bomb using the gun method, and they had the plutonium bomb using the implosion method. And so they blew off one of them in New Mexico, and they were afraid that the temperature might be so high that it would light the atmosphere on fire. And so Enrico Fermi, who was working on it, was actually taking bets on whether or not it would light the atmosphere on fire. And that didn't make a lot of the scientists and stuff that comfortable. You'd think that maybe they wouldn't do it, but no, they just had an evacuation protocol for all of New Mexico, just in case the atmosphere were lit on fire. And but that didn't happen, and so that Trinity test worked. And so then we had two bombs. Little Boy, which was a uranium-235 bomb, that was dropped on Hiroshima. And then there were something like 10,000 people that left Hiroshima after the bomb blast and quite tragically went to Nagasaki. And so the next bomb was dropped several days later, and it was kind of, they ran out of places to drop it. They had city number 1, something wasn't right, weather wasn't good enough. City number 2, no good there. And it finally got to the point where they were going to run out of fuel if they didn't drop their bomb. And so they decided, well, let's just drop it on Nagasaki. And so that's the story of why Nagasaki was the second city bombed, was that they wanted to get the plane back in one piece, and so they dropped the bomb on Nagasaki. And so this is a very sad, of course, part of our history, that we felt that this needed to be done. But hundreds of thousands of people were killed in those two strikes, and the power of the atomic bomb and nuclear energy in general was unleashed at that point. We bluffed them by saying that we were going to blow up a city a day until they surrendered, but we were out of bombs. So, we probably could have made another one in a few months, but nevertheless, they surrendered, and World War II was over.